तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In our series of lectures on basic electronics, let us now move on to the next lecture. Before we do that, let us recall what we discussed in the previous lecture. In the previous lecture, we were looking at some of the well-known theorems and laws which are very useful in electronics. Namely, we just reviewed the Kirchhoff's law of current and voltage, and then we also looked at in some detail the maximum power transfer theorem, which corresponds to when will maximum power be transferred from a given circuit to the load. We found that when that resistance, internal resistance of the source is matched by the external load resistance, there is maximum power transfer. We also saw some demonstration of the same. Lastly, we also saw the most important networks theorem, and that is superposition theorem. When we have more than one sources or current sources or voltage sources, how do we solve for the current or voltage across any of the given resistors? We saw what conditions are to be satisfied, how the whole thing has to be looked at as a superposition. So this superposition theorem is very useful in solving network problems. Today we will look at two more very important theorems of network, basically Thevenin's theorem and Norton's theorem. These two are also very, very useful in simplifying very complicated circuits and trying to understand the working of different circuits in electricity and electronics. Let us now take first Thevenin's theorem. We actually had a very brief idea about this Thevenin's Norton theorem in the previous lecture. At the end of the lecture, Thevenin's theorem is very useful, by which a complex circuit can be reduced to an equivalent series circuit consisting of a single voltage source, which is called V Thevenin, and a single series resistance, which is called R Thevenin, resistance of the Thevenins, and a load resistance RL, which anyway is there in the circuit. So any complicated circuit having any number of sources and resistors can be simplified by just having only one Thevenin source and voltage source and one Thevenin resistance equivalently. So that becomes much simpler to solve once we have this type of an arrangement, and you can see that it becomes a very simple means of simple to solve such a theorem. Now there is also another theorem, the second theorem, which is called the Norton's theorem, which is a dual of Thevenin's voltage theorem. In the Norton's theorem, instead of looking at voltage sources, which we will do in Thevenin's theorem, in Norton's theorem we look at current sources. That means any complicated circuit can be equivalently considered as having one single Norton's current source and Norton's resistance. So these two theorems are very useful in solving many problems in electronics and electricity. So I have shown on the screen, you can see there is a black box where you have it could be any circuit with a number of DC sources and resistances, and that is connected to one RL, the load resistance at the terminals A and B, output terminals of this black box. What Thevenin says is that the entire set of resistors and sources that you have in this box can be equivalently considered with only just two devices. One is the Thevenin's voltage source V Thevenin, and the other is the Thevenin's resistance R Thevenin. So this V Thevenin, one has to obtain the value of V Thevenin and the V of R Thevenin, a value of R Thevenin corresponding to any given circuit, and then the circuit, the simplified circuit, will just have only three components: the Thevenin's voltage source, the Thevenin's resistance, and the external RL that is being connected. Then it becomes very simple, it becomes a simple potential divider. If I want to know what is the voltage across RL, it is just a question of finding out what percentage or what proportion or what fraction of the voltage V Thevenin is appearing across RL, which is a very simple problem we have already solved. So now let me take an example of a circuit which has got three internal resistors, R1, R2 and R3, and RL is the external resistance between the terminals A and B. You have only one source, because to start with the example will be very simple with one with voltage source and just three resistors connected as shown in the figure. So our job is now to find out how to solve this using Thevenin's theorem, so that we should be able to obtain ultimately an equivalent Thevenin's voltage and equivalent Thevenin's resistance, which will replace all these voltage sources V1 and R1, R2, R3 combination. So we will see what is the theorem saying. This theorem says that you can measure the Thevenin's voltage. It can be done in two ways. One is by actual measurement, the other one is actually looking at in an analytical way. So let us see how we go about doing this. The first thing is we want to find out what is V Thevenin, let us say. Then all that we have to do is remove the load, that is what you can see in the picture now. The load RL is removed here, and you just connect the terminals A and B to a voltmeter and measure the open circuit voltage. It is a open circuit now because the circuit is open at this point, you have removed RL. So the circuit is open, that means infinite resistance here, and if you measure using a digital multimeter the voltage between the points A and B, that gives the effective Thevenin's voltage appearing at the output. So if you want to measure, it is very simple. Open circuit, this, that is remove the RL from the circuit and use a multimeter, measure the voltage across the output terminals A and B under open condition. That gives you the V Thevenin. Now let us look at analytically how we get Thevenin, how do we calculate the Thevenin's voltage. Now since the circuit is open at between A and B, you can see there won't be any current through R3, the resistance R3, because the circuit here is infinite resistance, the entire current will be flowing only through R1 and R2, and therefore whatever voltage you want between A and B, it will be the same as the voltage between across R2. For example, the voltage across R2 will therefore be the voltage Thevenin, V Thevenin. That is what is shown here on the screen. V Thevenin is equal to VR2, the voltage across R2, and this we can easily calculate from this circuit, because you can see you have a voltage source, you have two resistors, and you want to find out what is the voltage that will be developed across one of the resistor. This is a simple potential divider, and therefore you know V Thevenin therefore will have to be V1 multiplied by R2 divided by R1 plus R2, which is nothing but a simple potential divider arrangement, and you are trying to measure what is the voltage, the proportion of voltage across R2, one of the resistors. So we can see this is a V Thevenin, and this will be the effective equivalent voltage source that we should ultimately use after we simplify the circuit. So, we have now got V Thevenin. Next step is to obtain R Thevenin. How do we get R Thevenin? R Thevenin can also be easily measured by just measuring the resistance across the output terminal with RL removed, that is the open circuit resistance. So, how do we do that? Remove, before you measure the resistance, remove all source voltages and replace them with a short while retaining any internal source resistance. So, if you have a voltage source, you just remove the voltage source from the circuit, connect a short in its place, or because we assume the voltage source to be ideal. If the voltage source has got an internal resistance, then include only the resistance and remove the voltage source. Similarly, if it contains current sources, then you have to open the current source, and if the current source has got internally very large resistance, include the resistance in the circuit. So, you will have only resistances in the circuit. You would remove all the sources, whether it is voltage source or current source. So, now after removing all the sources, look in through the terminals A and B, the output terminal where the load was, and measure the resistance. That resistance is equivalent to the R Thevenin, Thevenin's equivalent resistance. So, you can see in the circuit, that is what I have done. I have removed the voltage source which was here previously, and I replaced it with a short. So, this point is connected to the ground now, because we assume that voltage source to be an ideal voltage source, almost nil internal resistance, and therefore, you are left with only the 3 resistors R1, R2 and R3, and RL is removed here, and you have A and B terminal which is an open circuit situation, and therefore, now if I measure using a multimeter the resistance between the 2 terminals A and B, that resistance will be the equivalent Thevenin's resistance. So, we have seen how we can measure the Thevenin's voltage and Thevenin's resistance. Now, we can also calculate in this simple circuit which contains only 3 resistors R1, R2 and R3, we can calculate what is the equivalent resistance. I am sure every one of you know about it. You can see R Thevenin is actually R3 plus the parallel combination of R1 and R2. Let me go back and show you. You can see R1, R2 are now coming in parallel, because these ends are the same for the 2 resistors, these ends are also the same. Therefore, R1, R2 are coming in parallel, R3 is in series with this combination of R1 and R2. So, the equivalent Thevenin's resistance can now be written R Thevenin is equal to R3 plus R1 multiplied by R2 divided by R1 plus R2. This is the effective resistance of the parallel combination of R1 and R2. You add it along, because it is in series with R3, this effective resistance is added with R3 to obtain the total effective Thevenin's resistance R Thevenin. So, this can also be measured by using a multimeter. We would see that later on. So, an example, let us take an example of the same circuit. I have just given some values to the various resistors. For example, R1 is 3.9 K, that is 3900 ohms. R2 is 8.2 kilo ohms, R3 is 4.7 kilo ohm, and RL is 3.3 kilo ohm, and V1, the voltage source, is 10 volts. So, I have just given some numbers for the resistors and the voltage. We will now try to solve numerically what will be V Thevenin, what will be R Thevenin, and with the R Thevenin and V Thevenin in position, let us draw the simplified diagram and calculate what will be the output voltage across the load VL. So, that is what we are going to now do as an illustration. So, you can see the circuit diagram now with all the values shown. R1 is 3.9 K, R2 is 8.2 K, R3 is 4.7 K, and we want V Thevenin. Therefore, you know what we have to do. We have to just bring a voltmeter and connect between A and B and measure if you have got a voltmeter, Otherwise, we can also do by actually working out, calculating the V Thevenin by the method that we already mentioned to you. So, we can, well, let us now, if we want to measure the, if we want to calculate the V Thevenin at the output, you know R3 will not contribute anything, because this is in series with the infinite resistance here, because you are now open circuited, the RL is not there, and therefore, the voltage across R2 is the Thevenin's voltage with V1 connected to R1 and R2 in series, and therefore, all that you have to do is calculate what is the V Thevenin, which is equivalent to what is the voltage across R2. So, let us do that. V Thevenin therefore will be equal to V1, the applied voltage, which is here 10 volts, multiplied by the R2 divided by R1 plus R2, because R1 R2 form a potential divider. And so, V Thevenin is equal to 10 volts, because V1 is 10 volts, and R2 is 8.2 K, therefore 8200 divided by 3900, which is the value of R1, plus 8200, which is R2. And if you simplify this, we get V Thevenin to be 6.78 volt. You can verify it with a calculator. So, V Thevenin we have calculated to be 6.78 for this circuit, which contains a very simple scheme of 3 resistors and a voltage source. Now, we have got the V Thevenin. We should now measure or calculate R Thevenin, which is the open circuit resistance across the load. Now, for this, what we have to do? I have already explained to you, we should just make all source voltages by a short. You replace the source voltage sources with a short, current sources with open, and include any internal resistance that may be present along with the voltage source. We generally assume the voltage sources to be ideal for this case, and therefore, just remove the voltage source, connect a short, and that you have very simple scheme of only resistors. And we will now calculate what happens, what is the effective resistance or Thevenin between the two terminals A and B at the output. Now, that is exactly what we have done here. You can, on this picture, R1 is 3.9 K, R3 is 4.7 K, R2 is 8.1 K. We have replaced the voltage source V1 by a short. We want to measure what is this. You can measure by using a multimeter in ohms range, that will directly give you the Thevenin's resistance. The other way to do is to calculate from this circuit. This circuit is a very simple circuit. Again, you can see R1, R2 are coming in parallel, and the combination is coming in series with R3. Therefore, the Thevenin's equivalent resistance can be very easily calculated. It is shown on the screen. R Thevenin is equal to R3 plus R1 into R2 divided by R1 plus R2. We have already seen that. In this case, it is R3 is 4700 ohms, 4.7 K, plus R1 R2 combination is 8200 multiplied by 3900 divided by 8200 plus 3900, and the effective resistance when you do the simplification is around 7.3 K. So, this is the R Thevenin. So, we have calculated V Thevenin, we have also calculated R Thevenin, and once we do that, we can simplify the original circuit by just having V Thevenin here, as you can see, and you have an R Thevenin, which you have now calculated for this example, and just you have to connect the RL, which is the ultimate load resistance we want to apply. So, now once we have, you can see all the complicated circuit has been removed and replaced with a very simple scheme of one source and one internal resistance of the source, R Thevenin, which can be equivalently taught. Now, we have to calculate what is the voltage across the load. That is what the problem we started with. So, you can see, because you have only two resistors now, R Thevenin and RL, with a one single voltage source, the problem becomes very simple. You have to just look at the voltage across the RL. VL therefore is V Thevenin multiplied by the potential divider arrangement RL divided by R Thevenin plus RL. With the value substituted, V Thevenin we calculated to be 6.78 multiplied by 3300, which is the load resistance 3.3 K, divided by the Thevenin's resistance 7.3 K plus 3.3 K of the load resistance, and when you simplify this, you get a value of about 2.1 volt. So, you can see we have simply replaced a very complicated circuit with the Thevenin's equivalent circuit, and that becomes very simple to solve. Now let us try to simulate this whole measurement. I have just shown you, I am going to show you on the screen a simple simulation of the experiment. You can see a breadboard coming over here, and the same circuit is put there. There is one 3.9 K, there is another 4.7 K which is R3, and the R2 is 8.2 K, and your load resistance is 3.3 K. That is connected to your voltage source on this side, and the output is connected to your multimeter on this side, and the circuit also for simplicity for reference is shown here at the bottom corner. Now you have to measure the Thevenin's. We will do both. We will measure and we will also calculate. Let us do measure Thevenin's voltage. Once I click, you know what we have to do? We have to open circuit. That means we have to remove the RL. So I go there and click on the RL. RL is gone. Now I will have to measure the voltage using the voltmeter. Before that I should switch on the power supply. So switch on the power supply, switch on the multimeter. Now start applying voltage by using these buttons, increase button. I will apply, let us say 10 volts, because that is what we started with. So I apply now 10 volts for this circuit and measure the voltage across the load terminal after removing the load, and you can see the voltage on the multimeter is 6.78, which is what we calculated in the previous slides. So the Thevenin's equivalent resistance is very simple. Just remove the load, connect a voltmeter, switch on the power supply and measure. You find it is 6.78. Okay. Now we have to measure the if you want to see how it comes, you can go and look at here. You can see the whole thing. If I apply 5 volts, the Thevenin's equivalent voltage will be 3.39. When you apply 10 volts, the Thevenin's equivalent is 6.78. Now we will switch off the voltage sources. We will go ahead to measure the Thevenin's voltage resistance with R Thevenin, for example. We will have to calculate R Thevenin. We know the rule. The rule is replace the power supply with a short. So when I click here, you find this point is connected to the ground by using a shorting wire, and the power supply is disconnected. Now I have only 3 resistors. The RL is removed. Under open circuit condition, I will measure what is the resistance here. So I will switch on only the resistance. So I will switch on the multimeter. Immediately you can see it comes into resistance mode, and it measures about 7.343 ohms. So this is the Thevenin's equivalent resistance, and the calculation is shown here. R Thevenin is nothing but R3 and R1 R2 in parallel combination. So now we have measured both the Thevenin's resistance and Thevenin's voltage. Now we have to go and measure what is the Thevenin's output across the load. So the circuit now is simplified. You can see the voltage is connected here, and there is only this 7343, that is the Thevenin's resistance. This is the Thevenin's voltage source. Now we will have to set it for 6.78 volts, and this is the load resistance 3.3 K. Now we will switch on the power supply source and the thing, and then you will increment. Immediately the voltage comes out to be 6.78, which is the Thevenin's voltage we have set, we have measured, and therefore I set this for 6.78, and I just measure the output voltage across the load to be 2.1 volt, which is what we calculated in the previous example. You can see that the output voltage is also shown in this table. Easily you can see that it is about 2.1 volt. Now we will switch off the power supply and the multimeter. We are ready to go and try the actual experiment. So now experimentally we will go and try the experiment. We will perform the experiment and then do the same measurement. So here I have the power supply. The power supply red and black lines are connected to this circuit, which is actually for simplicity I have shown the circuit here. You have the same circuit which I just now did. this is the voltage supply V1 10 volts, we will set it up here, and 3 resistors R1 3.9 K, R2 8.2 K and R3 4.7 K. The same resistors are shown here. This is R1, this is R2 and this is R3, and this is the load resistance which is 3.3 K, and this is the load resistance. So, the red wire is connected to this end, that is this point, and the black is connected to the ground line, common line at the bottom, and therefore the input is connected from the voltage source. This is, now I have to set this for 10 volts, and I should remove this and measure the voltage across this point using this multimeter in voltage range. Then I will be able to measure the Thevenin's equivalent voltage. Let us do that. So, for that I remove the load resistance. Therefore, under open circuit condition I have the multimeter. I will connect the one end to the ground. I will take the other end and connect it to the point where R3 is coming. So, this is the multimeter. Now, I will switch on the multimeter to voltage range. Now, I have connected to voltage range, put it in volts and connected to DC. Now, it is reading 0 because I have not switched on the power supply. I am going to switch on the power supply, and it is set for about 10 volts. So, this is around 10 volts as you can see on the screen, 9.9 to 10 volts, and 10 volts is applied with the 3 resistors. I have removed the load resistance and measuring the output resistance, output voltage is around 6.89 or so. So, we actually calculated a value of 6.78. We see here it is around 6.9. The difference is because these resistors are not the exact values as it is mentioned here. They have some 5% or 10% tolerance, and therefore the actual resistance value will be slightly different from the values that I have specified here, and therefore you get the actual voltage corresponding to this combination. But you can see it is very close to what we actually discussed. And now I want to measure, this is the Thevenin's voltage because I have removed the load and measuring the voltage output using the multimeter. So, this is the Thevenin's voltage V Thevenin that we have measured. The next point is to measure the Thevenin's resistance. For that, what we have to do? I will first switch off, and I should remove the voltage source and connect it by a short. So, I will take a small short wire, I will remove this red wire, I will connect that point where the voltage source is connected to the with a short. This is a shorting wire which has come in place of the voltage source, and I have to now measure, after removing the load which I have already done, I should measure what is the resistance. So, I should now change the multimeter to resistance range and see how much is the resistance. So, I will move it to resistance range, I will press here. Now, I have done that. So, the 3 resistors are there, and I am measuring the resistance using this multimeter, and I hope you can see the reading here is about 7.19 kilo ohms or 7.2 kilo ohm. We calculated something close to 7.3 kilo ohm, we are getting it at around 7.2 ohm, the 2 kilo ohm. That is why there was a difference also in the output voltage when we measured the Thevenin's equivalent voltage. So, we have actually calculated the Thevenin's voltage, we have also calculated the Thevenin's resistance. Now, I have to connect the load resistance and measure how much is the thing. So, I will again remove this short, I connect the load resistance 3.3 K once again, which I removed previously. Okay. Now, I will connect the power supply back. So, I have connected the load resistance 3.3K in the same circuit. I have connected this power supply also back after removing the short. Now if I switch on and measure the load resistance, I want to just measure the load resistance, I want to push it into voltage. So now I have connected the voltmeter back to voltage, DC voltage, and I have switched on. This is again around 10 volts, and what is the output voltage across the road, VL, across the road RL, the VL is around 2.13 volts as you can see, and therefore the load voltage is now 1.3 volts under the condition of all the resistors in place. Now what we will see is, we have calculated the V Thevenin, we have calculated the R Thevenin. Therefore now I am going to introduce the V Thevenin, R Thevenin only, and put the load resistance and measure what is the output voltage. If we again get 2.1, then we have solved the circuit. So let us now try to do that. What I am going to do now is take this power supply out and set here 6. We got around 6.3 or so, right, 6.2 volts. About 6.2 volts I have set it up. Now what I am going to do is, I have here a resistor which is a potentiometer, a variable resistor. Let us first measure what is the resistance of that potentiometer. So I will take the multimeter in resistance mode and calculate what is the resistance of the. Now it is around 7.8. I can adjust it to some smaller value. So it is around 7.5K. I think we calculated the Thevenin's resistance to be 7.3 or so. So let me make it to 7.3 by moving the potentiometer knob. So it is around 7.3K, right. So we have now set the Thevenin's resistance by using a potentiometer. We have set the voltage source to give an output voltage which is equivalent to Thevenin's voltage. Now I will connect this across that circuit, a smaller circuit, simplified circuit, and now I will measure what is the output voltage using the voltmeter. So I connected the voltmeter across the load 3.3K. This is the Thevenin's resistance. This is the Thevenin's voltage source. So I have discarded the original earlier circuit, and I have got only two resistors. One is the potentiometer, which I have set equivalent to Thevenin's resistance near about, and this is the load resistance, which is again 3.3K, and the voltage source, which is 6.2 or something, 6.2 volts, right, 6.2 volts. Yes. So now we will have to measure what is the voltage. You can see the voltage is around 2 volts. We calculated to be 2.1 volt in the actual situation, and therefore it comes very close to that. And I already explained to you whatever difference is because these resistors that we have used are not exactly equivalent to whatever the color code says. There is a tolerance variation. Therefore you can see the Thevenin's equivalent circuit also gives about 2 volts. This circuit also gave 2 volts when I applied 10 volts here and then measured the voltage across the load, and therefore you can see the whole circuit can be replaced by an equivalent Thevenin's resistance and Thevenin's source, and we will be able to simplify the whole circuit in an easy way. Now we have seen a very simple scheme in which I have used only one voltage source and 3 resistors. We can also take examples which involve more than one voltage sources and several resistors. So, I have now considered a second example which is more complicated. Here as you can see, it has got two sources, there is V1 here 10 volts and V2 here 20 volts, and you can see the polarity is also changed here, and you have number of resistances R1, R2, R3, R4 and R5, and this R2 is actually RL, I assume, and therefore what we want to do now is find out what is the voltage across R2 A and B. R2 is our RL, I have shown here. So, we want to know what is the voltage across this. That means what? I have to replace this entire block around this R2 by simply using two devices. One is V Thevenin, the Thevenin's voltage, and R Thevenin, the Thevenin's equivalent resistance. That is what we should do. So, how do we go about it? There are a number of ways to do that. The simplest way is, because you find with reference to R2 there is some circuit on the right side with one voltage source and two resistors, and on this side there is another voltage source and two resistors. So, if you look at this side, you can see it is similar to what we saw in the previous example, and similarly there are two parts of the circuit, the left part and the right part. So, we can try to see whether we can solve the Thevenin's equivalent circuit for the right side of the circuit and for the left side of the circuit, and then combine them together and then find the total equivalent Thevenin circuit. So, that is how we will do that. So, now what we do is we have to remove the load. I have removed the load here, open circuit condition, and I should measure the using a multimeter in the voltage range, the voltage between terminals A and B. That will give me the Thevenin's equivalent voltage, simple. So, by measurement it is very simple, just remove the load, measure the voltage across the terminals of the load using a multimeter, that is all. So, Thevenin's equivalent, that is a Thevenin's equivalent resistance voltage. And similarly, measurement of Thevenin's resistance also is very simple. Remove the voltage source by a short, this voltage source also by a short, and measure what is the resistance between A and B using a multimeter in resistance range. So, as simple as that. Now, but we will go ahead and then try to see how we can measure. So, I already mentioned to you, we will consider this in two parts, left part and the right part. So, let us look at, for example, V Thevenin 1 corresponding to the left part, V Thevenin 2 corresponding to the right part alone, considered together separately, and then combine the two together. So, now I have here the left part alone, the left half of the circuit, and so now you can immediately see V Thevenin can be obtained because there are only two resistors, they are forming a potential divider. Therefore, I can calculate what is the V Thevenin corresponding to this simple circuit on the left side. V Thevenin 1 is equal to V1, which is 10 volts in this case, multiplied by R4 divided by R1 plus R4, because R1 R4 form the potential divider arrangement. So, when I put the values of resistors 470 ohms, 180 ohms and 470 ohms, I get a Thevenin's equivalent voltage of 7.3 volts, 7.23 volts. So, this is the Thevenin's equivalent resistor voltage for the left side. Now, we have to find out what is the Thevenin's equivalent resistance, R Thevenin RTH1 for the left side. For that, we remove the voltage source, replace it with a short, and measure what is the resistance. So, if you now you can see in the circuit shown, I have removed the voltage source and connected with a simple wire, and I just have only two resistors, and these two resistors are coming in parallel, and therefore R Thevenin is nothing but the parallel combination of R1 and R4. So, R Thevenin is equal to R1 multiplied by R4 divided by R1 plus R4, and that is by substituting the values 180 ohms and 470 ohms and simplifying, you can see R Thevenin is about 130 ohms. So, that therefore, we have solved the left side of the circuit. R Thevenin is about 130 ohms, and the Thevenin's voltage is 7.23 volts, that is what we measured. Now, let us move on to the right side. In the right side, you have R3, R5 and the 20 volts power supply. we have to calculate what is the equivalent V Thevenin and R Thevenin to this side. So you can see the V Thevenin is again is very simple because there are only two resistors R3 and R5 coming in the circuit, and so V Thevenin 2 is V2 star R5 divided by R3 plus R5. Now this is minus 20 volts because the polarity is reversed compared to the other one, and multiplied by 560 divided by 120 plus 560, that is a potential divider arrangement you have, and the value is around minus 16.5 volts. So that is the Thevenin's voltage, and to measure the Thevenin's resistance, again you go by the same rule. You replace the voltage source with a short and then calculate the resistance across the terminal where you connect the load. So we can see what is the actual value, and then you can see in the circuit here I have replaced the voltage source with a short, and I have to measure what is the resistance between these two terminals, and this is nothing but the parallel combination of R3 and R5. R3 is 120 ohm, R5 is 560 ohms. So R Thevenin 2 for the right side is R3 star R5 multiplied by R5 divided by R3 plus R5. With the values of resistors substituted, it comes to around 100 ohms, 99 ohms. So we have solved for the right side of the circuit. There is a equivalent Thevenin voltage and Thevenin resistance, and now what we have to do is we have to combine the two, the left side and the right side. We should combine them together. So that is what we are doing here. You can see this is R Thevenin 1 and V Thevenin 1, and this side it is R Thevenin 2 and V Thevenin 2. I combine them, and that will be the equivalent Thevenin's circuit of the thing. So V Thevenin is V Thevenin 1 plus V Thevenin 2. Algebraically you should add. This is 7.23, this is minus 16.47 in this case, but they are actually aiding each other. It's like a series connection, and therefore the total resistance will be 23.7 volts. And similarly the resistance, I should connect them together, 130 ohms and 99, that corresponds to 229 ohms. Therefore I can replace the entire circuit, combination of both the right side and the left side, with a very simple R Thevenin and V Thevenin resistors, and in this case the R Thevenin and V Thevenin are 23 volts, 23.7 volts and 229 ohms. Now finally, to obtain the voltage across the road RL, we will put all the things together, V Thevenin, R Thevenin, and measure what is the voltage across AB. VL, the load voltage, is equal to V Thevenin, which is 23.7 volts, multiplied by the potential divider RL divided by R Thevenin plus RL, and when you do that simplification, you get it is around 9.38 volt. So we can actually put the circuit on a breadboard and measure once again as we have done previous case. So we have taken two examples, one a very simple example, another one slightly more complicated with two sources and multiple resistors, and we have seen how the equivalent Thevenin's circuit can be obtained for this complicated circuit. So this is a final circuit with the V Thevenin, R Thevenin shown. Now we will move on to the next theorem, which is Norton's theorem, which is a dual of Thevenin's theorem. Only difference is you make all the complicated circuit of the network that you have got by replacing it with a current source instead of a voltage source. In the case of Thevenin, you replaced it with a voltage source. In the case of Norton, you replace it with an equivalent current source, and there will also be equivalent Norton's resistance, just as you have a Thevenin's resistance. So I have shown on the screen any circuit with several DC sources and linear resistances can be simplified with a single current source IN corresponding to Norton's current source and a resistance RN, or in this case it is connected in parallel, therefore we look at it as a conductance GN if you want to consider. Rn is the resistance value of this parallel resistance, and this RL is anyway there. So the problem now is how to get IN and RN by measurement and by calculation. I take a very similar example as we did in the previous case with three resistors R1, R2, R3 and one current source IS1 to start with. you have an RL here connected between the terminal A and B. How do we apply Norton's theorem and obtain the equivalent Norton's circuit? So, what we do is, if in this case, if you want to measure what is the Norton's current source, equivalent Norton's current source, all that you have to do is remove the load resistance and connect it with a short and measure what is the short circuit current. Therefore, what you have to do is remove RL and connect a current meter in its place. The current meter will measure the current flowing through that terminal. Now, because there is no resistance, it is called a short circuit. Current meter is assumed to be 0 resistance, and therefore, what you measure is the short circuit current across the load terminal, and that gives you the Norton's current. In the other case, in the Thevenin's case, you measure the open circuit voltage across the load terminal after removing the RL. Here you remove RL, connect it by a short and measure what is the current flowing through that short, and that is the Norton's equivalent current source. And if you want to measure the resistance, all that you have to do is open circuit RL, remove RL and measure the resistance across the terminals, and that means Rn is equal to Thevenin's resistance V Thevenin, R Thevenin, both are equal. R Thevenin and Rn are equivalent because the method of measurement is also the same. So, now you can see I have in this circuit I have short circuited the load. I have removed the load, connected with a short wire, and we have to find out what is the current here. Because I have shorted here, this R3 is in parallel to RL. Because I have got a short here, R3 will have no current at all. All the current will go through the 0 resistance path rather than the R3, and therefore R3 is not to be considered at all. Once you remove the, because R3 is not effectively in the circuit, you find IS1, the Thevenin's, the Norton's current source is actually dividing here into two current component, 1 and 1 here, and this is the, so they will move in two, the parallel resistors divide current, that is what we see here. So, I have written the equations here, and so you can calculate the short circuit current IN, which is actually the Norton's current source, is actually obtained from the IS1, the source, multiplied by R1 divided by R1 plus R2. So, this is the equivalent Norton's current. This is obtained because IS1 minus IN, if this is called IN, this current will be IS1 minus IN, whatever is the difference that will be flowing here, multiplied by R1, that voltage across this should be equal to the voltage across R2, and R2 is IN multiplied by R2, that is the voltage across R2. From this simplification you would get IN is equal to IS1 into R1 divided by R1 plus R2 by using the current divider theorem, if you wish to remember that parallel resistors divide current. So, we have now got Norton's equivalent current, and we must measure the Norton's equivalent resistance or conductance. For that, what we do, we open circuit all current sources and short all voltage sources. We do not have any voltage source in the circuit, and measure what is the resistance across the terminal RL after RL is removed, AB. Okay. So, this is equivalent to the earlier Thevenin's consideration. So, that is what we have done now. Now, you can see R1, R2 are coming in series and it is in parallel with R3. So, the equivalent resistance therefore will be R3 multiplied by R1, R2, they are coming in series, therefore together I should take them, divided by R1, R2 plus R3. So, this is the equivalent Norton's resistance. So, we have determined Norton's resistance, Norton's source, current source, and therefore we can put the RL and complete the whole circuit. We can calculate what is the load current when RL also is in place. So, that can again be obtained by the current division. IL is actually coming from IN, with through resistances, two resistances coming in parallel, Rn and Rl, and therefore IL is In star Rn divided by Rn plus Rl by the current division theorem, or IL is In star Gl by Gn plus Gl, which is using the conductance, the reciprocal of the resistances. Now we will take an example which will perhaps illustrate this very simply. I have taken R1 to be 270 ohms, R2 is 220 ohms, R3 is 100 ohms, and IS1 is 10 milliamperes. Now IN we know is IS1 star R1 by R1 plus R2. So if you substitute the values, 10 milliampere multiplied by 270 divided by 270 ohms per 220 ohms, this gives me an IN of 5.5 milliampere, which this will be the short circuit current at the across the terminals of the circuit where RL was originally. So we have to find out Rn. For finding Rn, you know R3 and R1 plus R2 together in series are coming in parallel. Therefore R3 multiplied by R1 plus R2 divided by R1 plus R2 plus R3, and if you substitute the values of resistances we have taken in the example, you get an equivalent resistance of about 83 ohms. So I have now got the equivalent Norton's circuit. The Norton's equivalent current is 5.5 milliampere we calculated. The Norton's resistance is 83.4 ohms, that is connected in parallel to the current source, and RL is also connected in parallel to the entire circuit. RL is 100 ohms. Now we have to calculate what is the load current, load voltage, etc. Now again by using the current division, IL is equal to In star Rn by Rn plus RL, we know all the values. 5.5 milliampere is the Norton's current multiplied by 83.4, which is the Norton's equivalent resistance, divided by 83.4 plus RL, which is 100 ohms here, and the current is 2.5 milliampere. Thus the load current value is obtained using Norton's theorem. So this is the actual final circuit where I have shown the value of the Norton's current source 5.5 milliampere, Norton's equivalent resistance which is 83.4 ohms, and the load resistance RL, and the IL flowing through the load is 2.5 milliamperes. Out of 2.5 milliamp flows through that, the rest of the 3 milliamperes will flow through that. So if 2.5 milliamperes is flowing through the load resistance RL, you can also calculate what will be the voltage across the load, which is nothing but the product of these two, and the product is about 2.5 into 100, which is 2500 millivolt, because it is milliamperes, which is equivalent to 0.25 volts. So you can calculate the voltage across the load, the current through the load, and the all information regarding the circuit. It is very easy by using Norton's theorem. Now let me quickly go through the simulation for this. So here I have the same circuit. You have the different circuits, resistance 270 ohms, here you have 220 ohms, here you have 100 ohms R3, and this is your RL 100 ohms. You have multimeter, you have a current source here, and the circuit is also shown here. Now we have to measure the Norton's current, which is the short circuit current, and the Norton's resistance. We will do that in the simulation. Now Norton's current, let us measure. What we have to do? We have to we have to short the load. Therefore we have to remove the load. So go and click here. The load is removed. In place I have got the multimeter in the milliamp range, in the current range, and I have the current source here. Now let us switch on the current source and the multimeter. Now increase the current to 10 milliampere, because that is a current value IS1. Now I have 10 milliampere current, and you can see the current of the short circuit current is 5.51 as measured by the multimeter. So if you want to look at the calculation that is shown here, IN is IS1 star R1 by R1 plus R2, which is 5.51 we already calculated. So we have obtained the current Norton's equivalent current source. Now we have to obtain what is the Norton's equivalent resistance. For that, you know, if I have current source, I should open circuit. Therefore, when I click here, the connection to the current source is removed. That means it is open circuit here, and I just have the 3 resistors, and I should make use of the multimeter in resistance mode and measure the resistance. Let me switch on the multimeter. It comes in ohms range, and it is measuring 83.4 ohms. So this is the Norton's equivalent resistance. If you want to look at the values, you can see Rn is actually R3 coming in parallel to R1 and R2, and therefore the equivalent resistance is 83.4 ohms. Now we have calculated the Norton's current, we have calculated Norton's equivalent resistance, then we have to get the complete circuit with the load connected. This is the Norton's equivalent resistance 83.4. This will be, I will set here the Norton's current, and I will measure what is the current through the load resistance, and the you can see the circuit here. And now I will switch the current source, I will switch the multimeter, and you would find if I just connect here, I get 5.51 milliamperes as a source, and the current, series current measured by this is 2.5 milliampere, which is the value we obtained previously, and therefore, and the calculation can be seen in the screen. 5.51 multiplied by 83.4 divided by 83.4 plus 100 ohms gives me 2.5 milliamperes. That is what we got. So by simulation, we were able to do the Norton's equivalent circuit. So then this is the final circuit that we have got here. The entire block is removed and replaced by one Norton source and one Norton's resistance, and they are connected in parallel to the RL, the load resistance. So we have already mentioned that Thevenins and Nortons are the dual of each other. In Thevenin, we have got a voltage source V Thevenin and a series resistance R Thevenin. In Nortons, you have got a current source IN and a resistance Rn in parallel. Now you can see how to convert from Thevenins to Nortons or from Nortons to Thevenin. You can see the relationship between the Thevenins and the Nortons values. IN is nothing but V Thevenin by R Thevenin, and Rn is equal to R Thevenin, that I already mentioned to you. So the two circuits are equivalent. Similarly, if I want V Thevenin, I should, if I know IN and Rn, I should multiply IN by Rn, that will give me V Thevenin, and R Thevenin is anyway equal to Rn. Therefore, we can see that the circuit, they are all equivalent. In our case, for example, if I have 10 volts and 2K, the corresponding Norton's current, if I want, I should short circuit and measure 10 volt by 2K, which is around 5 milliamperes. So 5 milliamperes is the Norton's current, and 2K is the Thevenin's resistance. That is what I have shown here. So the Nortons and Thevenins can be easily converted from one to the other, and therefore both the theorems are very useful in solving different problems in networks. So we will conclude this lecture at this stage, and we have seen two important theorems in this lecture. One is the Thevenin's theorem and the other one is Norton's theorem. Now in the next lecture, we will look at one of the important passive devices, namely the semiconductor diode and its different types, and how it will be very useful to use in many applications in electronics. Thank you very much.